All right, why don't we begin the seminar today? So we have Allison Jaynes from the CU LASP today as a speaker, and she did her PhD at the University of New Hampshire and graduated 3 years ago. And then she came to LASP as a postdoc and is now a researcher. And her interest is in radiation belts and also energetic particles. And today she will give a presentation on the critical role of substorms and Whistler mode chorus waves in the energization of Earth's high-energy radiation belts.
Thank you. It's a mouthful. Okay, so most of my research career at LASP so far has been spent on the Van Allen probe, so that's what I'll talk about today. However, I have joined the MMS team within the last year and a half, and we have just such beautiful data from that mission as well. Energetic particles out at the magnetopause, in the tail, in the inner magnetosphere. So that's also something to look for coming out in the future. So I want to thank all my co-authors, and thanks for having me today. So my outline is going to look something like this. I'm going to go over Van Allen probes, although most of you are probably very familiar with this mission. Talk about the REPT instrument, or the High Energy Electron and Proton Telescope, a little bit. Then go into some signatures that we've seen of local acceleration in the Van Allen probe's era so far. I'll talk about the relationship between substorms, geomagnetic storms, and radiation belt dynamics, because there are some subtleties there that I'd like to highlight during this talk. And then I'll talk about a paper we published last year, a study of this accelerator mechanism and how you get from the very lowest energies in the inner magnetosphere up to these very high relativistic and even ultra-relativistic electron energies. And this requires the existence of both a source and a seed particle population. And then I'll look at some ongoing work that we're doing right now that's examining a new cumulative substorm index that sort of tries to correlate what we're seeing in the high-energy radiation belts with something that we can measure, for example, on the ground using ground magnetometers, looking at a cumulative effect of what substorm energy has on the system. So the fundamental questions I'd like for you to keep in mind, or I'd like to address during this talk, is first of all, what is the relationship between substorms and radiation belts? There's been a lot of work done on this in the past. I know this has been explored in great detail, but there's sort of another element to this, is how do we actually quantify this? So people have indicated that there is a relationship, but how do we actually quantify this, give it a number, possibly even use this to predict what we see in the radiation belts? And then the second question that I'd like to examine is, are substorms, in fact, the driver for effective acceleration events, and not just what you think of as the larger events, or the classic geomagnetic storms? So the Van Allen probe's mission has been a very high-profile mission, extremely successful. This is just an overview where it's showing the orbits of both spacecraft, which are identically instrumented. They're going around the Earth with a perigee of about 700 kilometers up to over 6 RE, or Earth radii, and they cut in and out of the Earth's radiation belts 3 times per day. They go through the inner zone, they go through the slot region, the outer zone, and they're phased such that sometimes they're right on top of each other or chasing each other, and sometimes they're actually on opposite ends of this orbit, or opposite legs. And so you can really look at temporal as well as spatial effects because you have these differences in the timing between the two identically instrumented spacecraft. And so the other thing to mention here is that for this talk, I'll be mainly focusing on the ECT energetic particle suite, the MAGICE instrument from the energetic particle suite, and the REPT instrument, as well as the emphasis magnetometer, from which we can gather wave data. And I'll show data from all those instruments later on.
So did they have to especially radiation harden the electronics of this?
Yes,
probe?
Absolutely, yes. Yeah. The big thing about these spacecraft is that they're in an equatorial orbit. They cut through the heart of the radiation belt. It's an extremely dangerous zone for electronics to be in, and they absolutely had to make sure that they were radiation hardened.
Those are ITAR items, I presume.
Some of the components, yes. So we won't go into those in detail, but yes. So I'm going to give you an overview of the SAMPEX versus RBSP or Van Allen probes era, because I like how this puts the RBSP mission into sort of historical context. This is from Shinlin's paper. I just like showing this because it gives you a good overview over 20 years of time during which we had the SAMPEX spacecraft. And this is showing you with L shell on the y-axis, so distance from Earth, further as you go up, and then time across the x-axis, and color indicates intensity. And you can see through the solar cycle here where we've gone through a maximum to a minimum, back up to our very weak maximum that we've had during the RBSP era. You can see how dynamic these radiation belts are. And then when you get to this little slice at the end, which starts about 3/4 of the way through 2012 to the end of this plot, that's what we've had for RBSP. So you compare, all these nice storms, all this great dynamics, and then you see that this very, very edge of this plot is what we've had to work with. And so it puts it into context as far as this weak solar cycle that we've been in. However, that's not to say that we haven't had an excellent view at the dynamics in the radiation belts. And that's because we have such beautiful, sensitive instruments that we can actually see the long-term dynamics, even though we're in a so-called quiet time for radiation belts. So here is the full Van Allen probes mission, 4 years up to September 1st, 2016, just a couple months ago. So we start from September 2012, and each of these panels is essentially a fiscal year. And we have the same format of L versus time with color as intensity, where all panels are on the same scale. And this is electron flux for the 4.2 MeV channel, which is extremely high energy. This is ultra-relativistic energies. And except for this quiet period during this year here, we see the just beautiful dynamics occurring, where you have very strong acceleration events that happen. You have very sharp, abrupt cutoff events where it looks like there's just a knife edge that has come along and wiped out the radiation belts. There's another one right here. Those are not instrumental effects, those are real. That's some kind of solar wind driving that has affected a total dropout across a wide spatial range of this energy. And you also see instances of 3-belt structures. So here was the Dan Baker paper here at the very beginning where we had this 2 outer belt structure. But you can also point to other places, for example, very recently in 2016, where you see a remnant belt lasting while a new belt gets created outside of that. So there's just such beautiful data set going on, and we're just going to look at a couple of events during this talk, but there's really a rich set of data to look into. And I also just want to touch on the 7.7 MeV, which is extremely high energy, and to show that there's less dynamics, of course, but there also have been some very strong events. I extended this plot to 5 years because you can see very recently we've had 1, 2, 3 strong acceleration events in the 7.7 MeV. This is just in the last 2 months, and these are the strongest intensities we've seen of these very ultra-relativistic electrons so far. Okay, so moving on to some signatures that we've examined of local acceleration occurring in the radiation belts using RBSP data. There was this nice Reeves et al. 2013 science paper, that showed this local peak occurring in electron phase space density. And because you're creating this local peak, it means that you're not seeing diffusion from outward piling in due to this inward radial diffusion, but you're instead seeing a process that's creating a peak at a specific location, at a specific L shell. And so this is indication of local acceleration or local heating of electrons via chorus waves.
Allison,
yes.
but I would argue that you continue to get inward radial transport to get it up by an order of magnitude more than the green.
That's correct.
Yeah.
So here you could argue for that strongly. But here where you see a very localized peak and you have this strong gradient on either side would be the signature of local acceleration, correct. So then March 2013 was another very nice event where we actually saw the phase space density increasing at lower L shells before it was increasing at higher L shells, meaning that there's something local happening. It's not just things getting moved from the outside inward. Okay, and then also Foster et al. Has some very nice observations of prompt local acceleration. At high energies, things are being accelerated very quickly, and this also points to linear or nonlinear interactions with chorus waves and high energy electrons. So the basic picture here that people have posited for some time is that you have a substorm injection or some kind of increased convection where you have injection of low energy particles into the inner magnetosphere. You have enough free energy, you generate these chorus waves. They can be very intense chorus waves. They interact with some of the pre-existing electron population in that region. And then you kind of grow that pre-existing population to higher energies than you had pre-storm or pre-event. So this is the basic picture, and it does all kind of hinge on how you get this energy source here and how you get this injection coming in to interact with what your pre-existing population was. So that leads into the relationship between substorms and radiation belt enhancements. So if we look first at electron response to solar wind speed, this was and is a very common way for people to try to correlate MEV electron flux at GEO or elsewhere with a solar wind parameter. Solar wind speed is used in a lot of our MEV electron models and forecasts, and so this is a common parameter to correlate with. And so I just want to go through some of the foundational studies here. Baker et al. 1979 showed that when you have a very strong solar wind speed increase, such as is shown here in this plot, you see an instantaneous increase in the lower energy electrons, which is this top trace. However, if you go to higher energies, this is at GEO, but it is the same, holds true in other places in the magnetosphere as well. If you go to higher energies, you see there's a lag time. So there's some kind of process that has to happen between when the low energy electrons get accelerated and when the high energy ones come in. And that's usually a lag of 1 to a couple days that occurs there. If you then try and plot, okay, what's the correlation between total radiation belt content or total electron flux at a certain energy at above an MEV with solar wind speed, as Reeves et al. Did in 2011 and Baker et al. Did in 2004, you get this triangular shaped distribution. And this has also been reproduced with Van Allen probes data. So this holds true to the best data sets that we have today. And the reason for this, well, first of all, what it indicates is that at any solar wind speed, you can have an extremely strong enhancement in electron flux. So you do not need high solar wind speeds to get up to these very, very high enhancements where you're going orders of magnitude over what you had pre-storm. You can have a very modest or even slight increase in solar wind speed and get this huge jump to very high electron fluxes. So this is not something that was anticipated at the time, but it's definitely been backed up by studies since then. And so people wanted to look into what exactly is the variation in this storm response, the variation in the outer electron belt. So Reeves et al. 2003, this is a very famous study, looked at the distribution in the response of greater than 1 MeV electrons to storm drivers. And so he took a data set over 11 years and actually looked at how often this pre-existing radiation belt population will decrease, and he plots that in blue, stay the same, no change in green, and then increase in red. And you can see this very normalized distribution where you cannot predict, for any given storm, you cannot predict if you'll have a decrease, no change, or an increase in your radiation belt content. He found almost no correlation between pre- and post-storm fluxes and no relation to DST. And this led to the famous saying of his that if you've seen one storm, you've seen one storm. You cannot generalize across storms. Brett Anderson repeated this study in 2016 I don't know if this paper is well known, but it should be, because he repeated this entire analysis using the exact same data set, but he looked at small storms only. So this was anything greater than minus 50 nanotesla. Some people would even classify those as non-storm times. And so he took all of that data and made a similar plot for just small or non-storm times. And look how similar it looks to the large storm plot. Again, you can have a decrease, no change, or an increase, and you almost cannot predict what will happen due to a very small storm. And I also want to point out the ratios here are very similar, meaning that for the small storms, you can get an increase by a factor of hundreds, and the same for large storms. Okay, so what about these non-storm enhancements? They've been reported on, especially in the Van Allen probes era. So Schiller et al. 2014 studied a non-storm time enhancement of relativistic electrons, and this is the plot I'm showing here on the left. You can see from the top there's Themis, mag ice from Van Allen probes, and then the little reptile instrument on the Colorado Student CubeSat, and they're all showing this intense increase in radiation belt flux right at the time of an extremely mild storm or a non-storm time where DST did not get below minus 30 nanotesla. So Su et al. 2014 also reported on a non-storm time event. And the same thing. They both attributed this enhancement to local heating via chorus waves, so what we just talked about before, that local acceleration process. But neither one of them actually emphasized in the paper that this was likely due to substorm activity directly. However, if you look at both of those events and take a look at one of the substorm indices, for example, AL here plotted here, you see that there was indeed a strong increase in substorm activity, followed by a prolonged moderate period of substorm activity during these enhancement events. So efficient acceleration events have several requirements, and this has been reported on starting with Meredith et al. 2002, when they suggested that only large storms that include prolonged substorm activity could actually give you an efficient enhancement event. So you need that substorm activity is what they concluded. Kataoka and Miyoshi actually found the main controller of outer belt flux was the IMF direction. And so you need southward BZ, which we know means increased substorm activity as well. They didn't follow it all the way to that logical conclusion, but they did indicate southward BZ was a necessity. Same thing with Shinlin, 2011, looking at MEV flux at GEO. They determined that southward IMF was a requirement. However, high-speed solar wind was not. So again, we're seeing that it's not necessarily tied to the speed of the solar wind, but it's definitely tied to that IMF direction, i.e. substorm activity. And then Wen Li in 2015 produced a very nice paper, which I'm showing a plot from here. She did a superposed epoch analysis of many, many events, which she broke up into efficient events and inefficient events. And you can see here that for different solar wind parameters, efficient and inefficient events can sometimes look very similar, especially if you're looking at the pressure or the solar wind speed even. You can see both increasing during the time of the start of the event. However, if you look at the chorus wave distribution, so these are the bottom two plots here, the top is for efficient events and the bottom one is for inefficient events. And you see for inefficient events, the chorus waves do not continue on into that period of when you would have acceleration. For the efficient events, you do. You have a prolonged period of chorus wave enhancements. And so you really do need that prolonged southward BZ, shown in this panel, and you need that chorus to occur to have efficient acceleration. Okay, so to summarize, we need that southward BZ. You can have a range of solar wind speeds. Almost any speed will do. You need continuous and moderate to high AE activity. It doesn't even need to be that strong. It just has to be continuous. And there's no restrictions on DST or other solar wind parameters. And so really, you just need that energy flowing in based on substorm injection. So you need something to kick off that process. So now I'm going to talk about an experiment that was kind of just set up by nature, and it allowed us to come in and look at something that otherwise we would not have been able to simulate or necessarily simulate or observe, except that we had this perfect event just kind of set up for us, and we were able to come take a look at what was going on. So this was in September of 2014. Now this is GOES data from geostationary orbit. This was an event that was actually noticed first by Howard Singer, and he kind of decided we should get together and figure out what was going on. But he noticed that the GOES data for the higher than 2 MeV channel and the greater than 0.8 MeV to some extent were pretty historically low. You can see they sort of bottom out here, and here's a zoomed in plot, so you can see that they basically go to the noise floor of the instrument, the greater than 2 MeV fluxes during this week of time. And they stayed there even though there was a high-speed solar wind stream, there was an increase in solar wind velocity, and on paper it looked like you should have a nice efficient acceleration event. So we dug into this a little deeper by using the Van Allen probe's observations. The nice thing about Van Allen probes, of course, is you get to look over a wide range of energies, so you have this very wide spectrum to take a look at. So we're going from mag-ice energies all the way down through rept energies, starting at 30 keV, going to hundreds of keV, 1 MeV, and then up through the ultra-relativistic energies. The portion that I have the box around is the time when we had that non-acceleration event. You can see there was a dropout at the time of the storm, and I'll show the solar wind data in a minute. And after that, things just never accelerated even back up to pre-storm levels, let alone higher to even greater levels. And the point here is that it was actually bracketed by 2 other periods of time, which were very efficient acceleration events. And once you look at the solar wind data, you'll see that these 2 storms here, which did produce a lot of flux at very high energies, look like HILCA events. And this stands for high intensity, long duration, continuous AE activity. So that means lots of substorms and continuous substorms throughout that entire interval. And so these HILCA events produce very nice acceleration up to even 5.5 MeV in both cases, but this one in the middle here did not. You'll see in a minute that this was a period of sustained northward BZ, and the substorm activity was almost non-existent. And therefore, you do not get the accelerator mechanism to kick in, and you do not get these very high energies to appear in Earth's radiation belts. So here's a look at the solar wind and geomagnetic activity indices for this time period. The top is a wider time range, and then I'm kind of blowing up just the non-acceleration event. And if you see what I've circled here is the solar wind speed, you have a very nice increase in solar wind speed at the time of this storm. And that alone would cause you to believe that there would be an increase in relativistic electron flux. And that's not, of course, what occurred. If you look at just the bracketed high-speed stream event, you'll see some differences if you compare it to the HILCA events. For example, AE here, very nice continuous AE activity, nice stream of substorms coming along here. And right here in the middle, just almost nothing. If you blow this up, you can really see this lack of AE activity during this 7 to 10 days of time. There just was almost nothing going on. If you take a look at the blown up BZ here, you can see why, because it was a very sustained northward BZ. Here, when you have this fluctuating BZ, you get lots of times when you have the IMF flipping southward, so you get lots of energy coming into the system, increased convection, and so forth. But when you have the northward BZ, none of that happens, and your substorms just stop. Okay, so you also have to look at the waves themselves, so you can't just look at solar wind data and extrapolate. So what we did was we turned to Wen Li, who had developed this technique that you can read about in her 2013 paper. And what she's done is create a proxy from POES satellite data. So POES is a low Earth orbiting satellite data that looks at satellite data set that looks at a lot of weather and other data for NOAA, but it also has some radiation belt environment monitors on it. And they'll actually give you the precipitating particle flux. And that's the key here. This is what she uses, is the precipitation at low electron energies. And she uses that to infer what the chorus wave amplitude is in the equatorial magnetosphere. And so it's a pretty cool technique, and it seems to work pretty well. She's compared her proxy with actual data from Van Allen probes and Themis and other satellites. But so what she's done here is reconstruct. Again, this is inferred wave amplitude, but she has reconstructed what the chorus wave distribution looked like across L shell and across time for our period of non-acceleration. You can see up here, from here to here, this just period of almost no substorm activity. In fact, here it's almost just a flat line at 0. And then if you look at the chorus wave distribution for both the sector that RBSP was flying in and the MLT average, so the full global picture, you can see that there was just absolutely no chorus wave intensity happening during this time at all. It was almost dead quiet. You see it pick up again at the very end here, and if you were to extend this plot, you would see this grow and grow until you actually have some decent chorus wave intensities, and then you get the acceleration in the electrons as well. So we came up with this picture of what the accelerator mechanism looks like for the inner magnetosphere. Here is our schematic where we have energy along the y-axis and time along the x-axis. And it's a little bit relative here, but this is the basic progression of events that you need. You have to start with your substorm injections and enhance your source and your seed populations. And in this paper, we define source as several to tens of keV electrons and seed as tens to hundreds of keV. And the reason for that distinction is you actually need both populations, which I'll kind of come back to our original plot and show you that in a minute. So you get the energy transfer from the source population to the chorus waves. So these very low energy electrons are actually what grow your chorus waves. You need a nice temperature anisotropy. That's created from your substorm injections. And those kind of give their energy over to the chorus waves and allow those to grow from that instability. And then you have those chorus waves interacting with your seed population. They accelerate the tens or hundreds of keV up to even higher energies through resonant cyclotron interactions. And finally, you end up with your enhancement of outer belt relativistic electrons that, if you give it enough time, can get to higher and higher energies, including multi-MeV energies. One of the keys to this picture is that you need the substorm injection process to happen in the background the entire time. So you can't just have one little period of enhanced substorm and then it goes away. You actually need to have this energy kind of continually feeding into the system, continually growing this mechanism, and then wait for a little while to get your ultra-relativistic electrons. So if we go back to that original plot very quickly, I just want to point out that now that we know the definitions of these electron populations, you can look and see that we didn't have any source electrons, much of anything, during this event. We did, however, have a nice sizable seed electron population. So we had actually quite a few hundreds of keV electrons hanging around and ready, waiting to be accelerated to high energies. But that didn't happen because we didn't have the source electrons because there was no substorm injections feeding them, and we didn't have the chorus waves acting on them. And so as a result, nothing got up to these higher energies. So this has a clear relevance to space weather forecasting, of course. If you look at the NOAA SWIPC relativistic electron forecast model for this event, you can see in green, this is the forecast, which goes 1 to 3 days ahead of time. The yellow is the observations at geostationary. And so the green, once we hit this storm I was talking about where we had a solar wind speed increase, you can see the green try and go up. So the forecast wanted the electron flux to really jump up. However, it was corrected because the yellow observations came in and said, nope, we're going down. The green forecast continually tries to jump up to these unprecedented levels, actually higher than pre-storm fluxes. but it just never happened. And so you can see where the observations in the model really diverge in a case like this. So it points to the additional information that we really need to wrap into our models in order to efficiently predict what's going to happen in the radiation belts.
So, Allison, I didn't get whose forecast model that is.
That's SWPC.
I know. So what are they using? Are they using Shinlin's? Are they using an Air Force one? What are they
So it's based on Shinlin's. It's except that it's a more simplified model based only on solar wind speed. Yeah. So Shinlin's model actually takes into account a little bit of the BZ and the pre-existing population as well, the pre-existing electron population. But this is based only on solar wind speed. And so, of course, as we've already gone over, it would fail in this instance.
So why do you think it's probably outside your pay grade or something, but why didn't they include the full model that included the BZ?
Oh, that's a good question. I mean, research to operations is a tricky subject, and I think that's a whole nother colloquium. Yeah.
I know, but they're not using
But events like this can actually prompt some of those people at higher levels to think, well, we really need to be including more information in our prediction models. Okay, so we can do a little bit further examination of this connection between substorms and radiation belt enhancements using the full Van Allen probes data set. So if you plot the electron flux in terms of long time periods, so this is actually over a year of data with a relative electron flux on the y-axis, but you take cuts at different L shells. So the red here is L equals 6, and then the blue goes all the way down to L equals 4. You can see what those relative increases and decreases are over a long period of time. If you then plot a very long period of time series of solar wind parameters and DST, it's very hard to find a way to correlate all of this stuff with what's going on in the radiation belts. And in fact, you can try and do this analysis, and it kind of comes out like a mess. You cannot correlate, especially the increases and decreases with any one or even two solar wind parameters or geomagnetic parameters. So the idea here was to look at what the substorm activity index could tell us about these enhancements. Obviously, it won't tell you much about the losses, but it can tell you something about the enhancements. So what you do when you plot now AE and DST, and then your electron increase and decreases, what you can look at is these times in which you had very low storm activity, geomagnetic storm activity. So your DST does not go very low at all during these times. You do have moderate to high substorm activity, but it's continuous as well. And then you'll see that these match up to these events where you actually have acceleration that brings your electron levels up to higher than they were, pre-event. And so instead of trying to correlate with DST, you start to pick out that actually these events are related somehow to the increase in the substorm activity. Now we've seen a lot of periods of weak substorm activity, but it's been prolonged, and you get that acceleration eventually. Now, developing a metric that you could try and correlate with what the AE is doing is very difficult. Well, it's not difficult, but it's not straightforward because, AE is going up and down, and the electron flux is not responding like that. You need to have some continuous increases to get eventual acceleration, but when AE goes down, the radiation belt content does not drop at the same time. Okay, so there's not a loss process that is related to turning off the substorm activity. It's only a matter of turning it on and seeing that acceleration start. So you can't just do a linear correlation between AE index and radiation belt intensity. That just won't work. So what we tried to do instead was look at what we're calling an accumulative substorm index. So it's very simple. We just implement a cumulative sum from the AE data. We've also been looking at AL as well. And this just takes your original data set, and then you just add one element to the previous one to get your current element. So you start with A, B, C, D, and then you get A plus B, A plus B plus C, and you continue to ramp up in that fashion. Now the issues that we had. There were several issues that we had trying to understand this process, and we actually had a student working on it this summer, an REU student, and she did some great work. But there's things you have to decide, such as what are you going to trigger on for starting that index to accumulate. So we decided we would try rise of electron flux by a certain amount or a ratio, but then you also have to decide when you're going to stop that process. So you can't just accumulate data. You can't just cumulatively sum things forever, because electron flux doesn't go up and up forever. There's times when the substorm activity dies down and loss processes take over. So you have to decide on when you're going to kind of cut off that cumulative index. And this we decided to do when the electron flux decreases by any amount. So essentially, the electron flux is going to start to rise. We start to accumulate our index. And then when it starts to decrease at all, we just cut it off and say, okay, we've done the enhancement. We don't know what's going to happen for the loss. So we tested our modified AE index, is what we called it, on 3 different electron acceleration events. We included a variable time lag because, like I mentioned, you can have this process does have a time scale, and so you can have things that are taking 1 to 2 to 3 days before things really start accelerating and before you see these enhancements. So we had to include a variable time lag in there. And then our limitations, of course, is that this is really only useful for correlating or predicting electron enhancements. So we don't have any information about the loss, and we're not accounting for any loss processes. This is strictly about trying to figure out what's happening during the enhancement or acceleration process. So here's some of our events. We're going to start with August through September of 2014. And what we've done for all of these cases is plot electron flux over time for a certain energy channel. Here we're looking at energy channel 3, or about 3.5 MeV. So you can see the intensity over time, and it goes up and down. There's clearly an enhancement taking place here, as well as at the end of September. And in fact, if you remember the event I showed a few slides ago, here's our quiet time in September in here. But there was an enhancement event at the beginning and at the end of September. And so the next panel will be our modified AE index, which I'll come back to in a second. The last panel is just the straight AE data. So this is the very highly fluctuating data. It goes up and down. However, you can see by eye, first of all, that when you have a continuous string of these enhanced AE index clusters, then you get an enhancement in the higher energy electrons. So what the middle panel is showing is that cumulative sum of this AE index on the bottom. And again, we've started to sum it when the electron flux starts to rise. So here will be a case of when we triggered it to start summing. And then when the electron flux starts to go back down, we don't know what's happening over here. We're not including loss processes, so we just kind of cut off that cumulative index. And you can also see here at the beginning of the period, at the beginning of August, that we're seeing a little bit of cumulative substorm activity. And then at the end, of course, we're seeing another bit of cumulative substorm activity. But this is quite nice because, really, if you look at this bottom panel, it's a little bit hard to say what's going on. But if you look at this middle panel, you can see quite easily that there's a period of enhanced substorm activity, a very large period of enhanced substorm activity, and then a more moderate one at the end of the month. So when we do the linear correlation with our electron flux and this modified AE index, we actually come up with correlation coefficients. Well, for this example, it's 0.9, which is incredibly good. There's no single solar wind parameter that you could use to correlate with this that you'd come up with that same level of correlation. So we were quite surprised by this result, and I think it looks really good for trying to refine this into something that's actually usable to indicate or predict radiation belt enhancements.
Excuse me. So,
yeah.
What threshold do you use to do the cutoff, or where do you?
Yeah. So it's anytime the electron flux starts to decrease, and there is a certain amount. Obviously, there's noise in the data, so you don't want every little decrease to make it cut off. So there's a certain threshold that we kind of played around with till we till we got what we thought was the right amount. But here you can see where this red line is, for example. So we're picking out this specific event. And where this red line is, you can see that after this, the electron flux starts to decrease and loss processes take over. And again, we're not able to say anything about we know what's causing that loss probably, but we're not able to say anything about how the substorm index or substorm activity relates to that loss process. So here was another very famous event, March 2015, in which we had a very strong relativistic electron enhancement. We also had extremely strong substorm activity for this event. And once again, you see that as the electrons rise and your substorm activity increases, and if you add that all up and form a cumulative index, you can actually get this to correlate with your electron flux with very high correlation coefficients. So that was another event that we looked at. This event and actually the one previous to it are both a little complicated because of this dropout here. So I don't know if anyone's noticed that this happens quite often, where you have this dropout at the beginning of the event and then your acceleration starts. And so we haven't treated this dropout. We're just kind of skipping over it for now, because that's something that, again, we can't really make any assumptions about in the context of substorm activity.
But that dropout is due to inward motion of the magnetopause for these big storms.
Yeah, most likely. Yeah. Although it depends on what L shell you're looking at. Yeah. So then we're going to go to just the final event, October 2015, in which we had another enhancement event. This one was a little more complicated because you had sort of some up and down clusters of substorm activity, but we're still getting correlation coefficients that I think are better than we ever expected. So we're sort of in the middle of this work, and I think it's looking very promising. And then I also wanted to talk about a related study. This is something that Hong Zhao has been looking at, and this is using the REPT and MAGICE data from the entire Van Allen probes mission so far. And what she's done is look at the relation of the electron flux enhancements and the solar wind parameters and geomagnetic indices, and making some plots similar to the scatter plots I showed at the very beginning of the talk, where you're trying to relate electron flux to something, solar wind parameters or even substorm index. And what she's done is done a very simplified model of a flux enhancement, or a condition for a flux enhancement, where she's just taking daily averages and then looking if the flux has increased from one day to the next, calling that an enhancement, and then plotting it with respect to different solar wind parameters and geomagnetic indices. So for this cluster of plots, for mu equals 1,000 MeV per G, and this is at L star equals 4.5, so very firmly in the heart of the radiation belts, she has found kind of what you'd expect, this triangular distribution that we saw before, where at low solar wind speeds you can have high enhancements. As you go up in solar wind, it's much more likely that you're going to get a high enhancement, but you can kind of get that at any speed, and so you get this triangular distribution. But the most interesting thing I think about these results is that she has found the highest correlation for high mu electrons actually occurs with AE. So kind of what we've been showing all along is that you can't correlate it very well with lots of other solar wind parameters, but if you just look at AE, you actually get a very decent correlation coefficient. She found up to 0.8 with a time lag of 3 to 5 days. And again, these are very high energy, so that time scale, you have to kind of wait for that time scale to take effect before you see this acceleration. And this is under review right now, so hopefully it'll be out soon. Look for it. Okay, so then I'm going to just give you my summary. So using a range of satellites in the system, we actually have investigated relativistic electron enhancements and that mechanism that makes those happen. And so what happens when you have a piece of that missing, for example, the source electrons and the chorus waves are missing, then you don't get an enhancement of relativistic electrons. So we need both the source and the seed populations. You need those VLF waves, and you have to have this whole progression in place in order to see that enhancement. And the missing piece here, or the crucial piece here, I think, is the substorm injections. And those can really constitute a breakthrough in our space weather forecasting and modeling if we can find a way to efficiently implement them into the models. And a modified index that I've showed some preliminary work on actually takes into account not just substorm activity, but the cumulative effect. So how it adds up over time, and that correlates very well with our radiation belt enhancements. And so the last statement I want to make here is that I really think all the communities should look toward substorms as a driving force behind energetic electron enhancements and not just focus on geomagnetic storms. Thank you.